I am Avinash. Now I am going to present my MS research topic, which is suspended gate FET. For that, SE analysis and noise modeling using lookup table. First, the content will be like this. First, I will give the overview, and after that, the device structure and what is the research motivation for that, and I will explain also LUT based framework, in which I will also give DC characteristics and small signal model validation, and after that this model validation is also going to be used in the LUT based model for the SGFET, and after that the next content is noise analysis and simulation. Then I will conclude. The overview is like that. MEMS structure mainly integrate non-electronic and electronic component for the sensing and processing and actuation control. The commonly used in the MEMS devices for transduction, piezoresistive, piezoelectric and capacitive, and among them capacitive MEMS offers high sensitivity, but requires large area and a complex interface circuit. Because of that, to overcome these problems, SGFET is the alternative, which enables the direct displacement to the current transduction with high sensitivity and reduced capacitive load, and it also supports the monolithic CMOS MEMS integration. Now the device structure will look like this. In the there is a air gap between the movable gate and in between the channel, and there is also stacked up the like air gap and thickness, oxide thickness, and now the because of the air gap, it can displace the gate because of the external forces like any excitation, acceleration, which can modulate the channel width and effective gate capacitance. And if it is modulating the effective width, then it is going to also modulate the channel current, and it also enables the electromechanical sensing operation. Now the LMGFET is one of the configuration of the SGFET. In this configuration, the gate moves laterally in y direction. If it is moving laterally y direction, and at that time the channel length and air gap is going to be constant, but the effective width is going to be changed. According to that, the current is also going to be changed, and this current will be linear to the width of the effective covered width of the device. Now research motivation and problem statement. The research motivation is that SGFET enables the direct displacement to the current transduction with the higher sensitivity and reduced capacitive loading, and the configuration of SGFET LMGFET means laterally movable gate field effect transistor also improves the linearity and dynamic range, and in this device also going to be consider the noises like thermal noise and flicker noise for the performance of the sensor, and this device also going to be unified, give the unified compact model including the AC and noise behavior, which is unexplored. The problem statement is going to be like this. The existing model of the SGFET did not focus on the incorporated the noise mechanism in the device. Now in this model, which is I am going to present, it will unify the physics framework with the AC and noise analysis, and which will also enable the circuit level simulation. And how it is going to be modeled? It is going to be developed first the LUT based SGFET model, which will also going to be simulated for the DC, AC and noise simulation, and for the circuit analysis. The using of the LOT model, because it provides the simpler and faster alternative to develop the develop the model for a circuit simulation, which will take lesser time the other than the compact model. Now, how SGFT based sensing will work? It will be means the input will going to be either acceleration, either electrical force, electrostatic force, which will going to be to the differential amplifier. In the differential amplifier, the SGFT LOT based model is going to be taken, and this differential amplifier will generate the signal, which is going to be controlled by the controller. Now, when because of the input acceleration, the width of the device is going to be fluctuate, means displace. Then for that displacement coming to initial point, for that it needed actuator, and actuator needed higher potential. That's why charge pump is also feedback for the providing the higher potential. Now, I am going to give the LOT model framework for the DC, AC and noise simulation. The general case for the LOT based model for using this one is it is providing like for the complex devices it is faster, and what LOT based approaches do, it stores the device characteristics in the tabulated form, and it also enables the fast model development for circuit level simulation. How it is going to be flow? The first there will be the setup for the device, and then the dynamic data and static data is also going to be extracted from the device, and both the data is going to be stored in the form of LOT, and both the static and dynamic data will be stored in the LOT form. Then it is going to be given to the simulator like a cadence. What lookup table contains? It contains the IV tables, which is the function of the gate and drain potential. Also the dynamic data like QV, which also is function of the gate potential and drain potential, and how it is going to be computed in the simulator. It will give the DC, means static and dynamic current with the equation of given below. Now, LOT based model validation for DC and AC analysis simulation. Before going for SGFT, first we validated the DC means LOT model for a test device, which is the test device is taken as a GPTK 180 nanometer NMOS, for which we are going to extracted the DC and AC simulation, and from there the gain, bandwidth and frequency response is also simulated. Then from the test devices simulated DC and AC characteristics, the characteristics of this is going to be stored in the form of the tabulated form, which is going to be LOT, and this LOT is going to be stored going to be given to the Verilog A, and this Verilog A will simulate with the simulator, and then both the result of the for the same biasing condition is going to be compared. Now, the result of the simulation, first one is the dotted line is showing the for the test device, which is coming from the LOT. The solid line is showing which is the from the test device without LOT. Both are showing the closed mapping. In the means in the input characteristics, also in the output characteristics. Now, for the small signal model validation, it can be performed in the two ways, two approaches. First one can be the capacitance based LUT, and the second one can be the charge based LUT. In the capacitance based LUT, the small signal current is going to be biased with the help of the GM and GDS, and the for the bandwidth, for the accuracy of bandwidth, the extracted capacitance is going to be included in those model, and from there the small signal current is going to be extracted with the equation of this dCV by dt. And in the charge based LUT, it will directly extract the terminal charges from the simulator, and it is the small signal current is going to be simulated with the help of dq by dt. And in the case of charge based LUT, it ensures the charge conservation, which is going to be preferred for the analysis. Now, it is charge based LUT is also consistent with in the dynamic behavior. I am going to show the why charge based LUT is consistent. First, the setup of the small signal. The setup for the small signal model is the self bias configuration. In this configuration, the component RL and RLC is taken higher value, and in the DC case, in the component L will be sorted, and from the path of the through the sorted L, it is going to charge the capacitance. It will charge till the when until the gate and drain potential current is not going to be same, and in AC case, the charge capacitance will provide the biasing point to the test device. For that, the result is with the capacitance based LUT is shown here. First, taken for the different step size of the VD, which is first it is a 0.1 volt, and in this case the gain error is nearly 3%, and but in the bandwidth error is nearly 13%. And when the step size of the VD is reduced, in this case the gain came nearly 2%, and the bandwidth error was increasing, it was nearly 15%. Again the step size of the VDS has reduced, then again it is the there is a gain improvement, but not in the bandwidth improvement. So that it tested with the also charge base, which shows that for the same step size of the VD, it shows the there is a similar behavior in the gain, but it shows the good improvement in the bandwidth. Now, which shows from the plot also, which is showing the close agreement between the LUT and GPTK NMOS. From here we have gone means we have validated that charge based LUT is better, and now for proposed LUT model, we are going to implement in the SGFET, which will also enable the efficient circuit level simulation. Now, I am going to show LUT based model implementation for SGFET. It will go in the same flow from in this case, in the case of SGFET, the device is first done in the TCAD, synopsis TCAD. From there, dynamic and static data is going to be stored in the form of LUT, and the LUT is also going to be given to the simulator. In this case, the simulator is cadence. Now, this DC characteristics has been also done with our group member Pramod and Ganga KM, and I am repeating this simulation because of the validation purpose. The device parameter is given here. which is shown it is the substrate is p type and the lower doping and all other parameter is given. In this case the device is 2D structure, that is why the width is normalized to the 1 micrometer. How in the device air gap is modeled, it is modeled with the relative permittivity given as 1, which is vacuum permittivity. Now the air gap decided by the optimizing multiple simulation at the nearly 200 nanometer, it shows the good behavior of the gate control of the device. That is why the air gap is taken as the nearly 200 nanometer. The extracted VTS threshold voltage for the device is 0.21 volt, and it is also validated with the MATLAB plot, which is the maximum transconductance using maximum transconductance behavior. Now the same validation has been done from the TCAD to the LUT, which is showing the IV characteristics is closely matching with the device, and it is also showing the showing the conventional MOSFET behavior and it which is matching with the TCAD result. The solid the dotted line here is the for the simulation from TCAD, and dotted line solid line is from LUT, and dotted line from is the TCAD simulation. Now intrinsic capacitance of the device is also extracted. In this case in the conventional MOSFET the CGS is higher and CBS is lower, but in the case of the SGFET the CBS is going to be higher and CGS is lower because of the C effective and the permittivity of the silicon and oxide. And both also the intrinsic capacitance also matched with the conventional MOSFET. Now the same AC simulation has been performed for the SGFET for the same biasing condition. In this case the bias current is given nearly 93 nanometer, and the overdrive voltage was 0.8 volt. In this case the intrinsic gain was coming 25.6 dB, and the bandwidth calculated as 6.8 megahertz, 87 megahertz, and the simulation result for the AC simulation is shown here, which is showing also the means deviation from the analytical and LUT simulation. In this case the there is a small error deviation in the gain case, but there is a nearly some error more error in the bandwidth case. Now I am going to analyze the noise for the device SGFET device. There in the normally in the MOSFET the mainly two types of noise contains. First one is the thermal noise, and second one is the flicker noise. Thermal noise comes due to the random motion of the charges and transconductance also, and the flicker noise comes due to the charge tapping and the typing and detyping of the carrier also. It and also comes due to the mobility variation. The flicker noise depends on the device area and the drain current, and inversely proportional also to the frequency. Now from the TCAD simulation it shows the noise behavior of the device. For the SVD it is initially flat because of the generation recombination of the charges, and in the lower frequency which is nearly from 1.1 Hz to 1 kHz, and in SVG case means power spectral density of gate, it is showing first for the lower frequency it is increasing case. It is because of the induced gate noise which is directly proportional to the frequency, and after that at from 1K to the 1 megahertz it is showing the 1 by f behavior, means flicker noise behavior, and beyond the 1 megahertz to the 10 gigahertz it is showing the thermal noise behavior. and beyond 10 gigahertz it is showing the roll off in the noise which is coming due to the because of the RC filtering. Now it is tested with also with different oxide thickness. Left side is showing the with the oxide thickness of 2.5 nanometer, and the second right side is showing the for the thickness oxide is 10 nanometer, which is showing the small decrease in the noise behavior. Because of the, if noise thickness of oxide is increasing, means the coupling of the trapping and detrapping is going to be decreased, which shows the power spectral density is also going to be decreased. For the in noise behavior in the cadence using the LUT, it is shows the flicker noise is dominating nearly till 100 hertz, and beyond that the thermal noise is going to be dominated. Now I am going to conclude. The SGFET model is developed with the LUT based model of developed for the SGFET, and it is also validated reproduces the DC and AC and noise characteristics, which provides a efficient framework for SGFET MEMS sensor and for the system integration. What can be the future work in the at the device level? There can be the improvement in the linearity of the device, and reduction in the intrinsic noise of the SGFET, which can enhance the performance, and at the case of the circuit level, it can be incorporated in the for the sensor readout circuit, which can calculate the noise signal to noise behavior, bandwidth and resolution. And in the case of this interface of the circuit, it can be also used as the CV converter, means capacitance to voltage interface circuit. These are the practical aspect of the device. Thank you for the here. If any question.